In this video, we are going to be talking about probability and combinatorics, so let's get started. So this entire math counts lesson is going to be based off of probability and combinatorics, and we are going to start off with permutations. I'm going to let everyone know who's watching the lesson that probability and combinatorics is not based off of memorization and blindly memorizing the formulas. If you're going to solve a problem involving permutations and combinatorics, you need to understand what's going on in order to solve it. As you will see in the problems, blindly memorizing formulas will not often get you the answer when it comes to these problems. So let's get started with permutations. Suppose I have the letters A, B, C, and D. How many ways can I arrange A, B, C, D if we are only using repetition is not allowed? So we can't have something like D, 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 A. This is not allowed. But something that is allowed is B, C, D, and A. We're looking for all permutations of A, B, C, D. When we ask for all permutations of A, B, C, D, all the ways we can arrange the letters A, B, C, D to form different words. That's what we're asking when it comes to this. And we might just start listing them out. So we might have A, and then we can have B, and then we can change the last two. We can have B, D, C, then we can have B, C, D, A, then we can have C, D, B, A, or we can have A, B, D, C. We already did, and that's just a repetition of that. We could have A, B, C, D, but then we'd have to, okay. So we obviously see that this is not going to work out. Blindly using the brute force solution will not work in this case. We will need to come up with a faster way to handle this problem. Now, first off, let's look at this problem by constructively counting the number of ways we can build A, B, C, D using the letters only once. So we can't have A, or A, B, A, C, something like that. We cannot repeat any letter once. Okay? So how many choices do we have when we're constructing our permutation? How many choices do we have for the first letter? Well, you look, we have 4 choices. We can use any 4 of these choices, right? All right. Now let's say we choose C. We already chose C. Can't repeat it any time in our permutation. Now we need to choose another one. How many options do we have? We have A, B, D, 3 options. Let's say we choose D. Now let's go over here. Let's say we chose D, and now how many choices do we have to choose to build our permutation? We have A or B, which is 2 choices. And let's say we chose A. If we chose A, can't repeat it ever again in our permutation. We have 1 choice, B. Now, notice this. Check this out. To find the number of ways we can arrange these letters to form permutations of the same word would be, we have to multiply them, because for every 4 options here, there are 3 more options to pair it with. So we multiply. And notice that this, well, if we compute this, 4 times 3 times 2 times 1, 4 times 3 is 12, 12 times 2 is 24. This is a factorial. 4 factorial is the number of permutations. And as you can see, we can apply this to any permutation problem, right? I'm going to give an example. If you want to find the number of ways we could arrange, let's say, A, C, X, Y, Z, D. Well, for the first letter, when we're constructing this, we have 1, 2, 3, 4, 5 choices, right? If we picked something like A, we have 4 choices. Can't repeat it, 3 choices. And we keep going down until we hit 1. And obviously, to count, we multiply. We see this is just 120 ways, which is also 5 factorial. So we're noticing a pattern. Every time we're seeing the letters, in this case we have 5 letters, 5 factorial. In this case we have 4 letters, 4 factorial. Right? So we see we have a formula. If we have n letters in a word, the number of ways to arrange these letters to form new words would be n factorial. Now our formula is not all we expected, because as we'll see in the next example, sometimes permutations require more work than just filling in, finding the number of letters in the word, and then just placing a factorial at the end. Let's go on. Let's continue permutations. This time, let's see how many ways can we form A, B, A, C. How many permutations can we flip all the letters around to form A, B, A, C? Now you might just go ahead and say, hey, we have 4 letters, 1, 2, 3, 4. This is just 4 factorial. That's what you might say. Now let's see if that's actually true. We're not going to count every single one, but I'm going to prove to you why it's not true. Let's say if we decide to have permutation A, C, A, B, but then 4 factorial is saying for each letter we have 4 choices, right? 4 choices. Let's say we choose A. Now we have 3 choices. But if we choose A again, if we flip them over, it's the same permutation, because the A's are the same thing. This is the same exact thing. Let's say if this is like A1 and this is A2, this is the exact same thing. Of course, this time it's not the exact same thing, but the A's can be flipped in a way such that it's the same exact thing. So we have a problem here. We have repeated elements. And obviously this is all wrong. There's not 4 factorial ways. Now 4 factorial is involved in the problem, I'll tell you that. There's a 4 factorial in the problem. Check out the A's. There are 2 of them. Assuming the A's were different, how many ways could we arrange the A's? Assuming they were different. And that's just 2 factorial. Or 2 ways. Now let's take a look at the problem over here. We have A, B, A, C. Notice how when we have the 4 factorial number of ways to do it, we're just counting everything 2 factorial times. Because we're repeating the A's, we're swapping the A's around even though it's the same exact permutation at the end. So we need to correct for the overcount that we have up here. And we do that with some simple division. How many ways are there to arrange the A's if they were different? That's 2 factorial. There are 2 factorial ways to arrange it if they were different. And we can just compute this, and we'll have the answer. So we have 4 factorial is equal to 24. 2 factorial is 2. Computing the quotient, we get 12 permutations of A, B, A, C. Now, what if we had something like this? Now notice the b's are different. This time, the first thing we do is we overcount. 1, 2, 3, 4, 5. 5 factorial. But this is an overcount, so we have to divide by the correction. So the correction, let's see the correction. First off, we know we're going to have a 2 factorial since the a's. Now, we have the 2 factorial. You might just say it's 4 factorial because of the b's, but that doesn't make any sense. Because again, we run into the same issue where we're counting everything multiple times. Now, how many ways are there to arrange the b's if they were different? Now, if the b's were different, there's 2 factorial ways to arrange them. Same thing, 5 factorial is 120. That accounts for 2 factorial multiplied by 2 factorial ways. 2 factorial is 2 multiplied by 2. So we have 120 divided by 4, which equals 30 permutations of this word. Obviously, this is something you need to watch out for, is restrictions. Now, let's move on. We've discussed permutations. Let's talk about geometric counting. Suppose I have a circle. How many ways are there to arrange these seating options? How many ways can I arrange 4 people at this round desk, round table? Now you might just say, well, there's 4 things, 4 factorial ways. You might just go ahead and say that's 4 factorial ways. And you would be right, except let's rotate this a little bit. Now, if we rotate this a little bit, we can see that the rotation has some overcounting in it. 4 factorial is overcounted because we're rotating this and we're counting everything 4 times. Since if I rotate this a little bit over here, if I rotate it like this, in this direction, I'm going to get the same exact thing twice. Not only twice, I'm going to get 4 times since we have 4 seats. So what do we do when we have overcounting? We divide by the correction, which is 4 factorial over 4, which is 24 divided by 4, which equals 6. So there are 6 ways to arrange them on the table. And remember, geometry matters. With geometric counting, you have to look at the physical figure and decide how many ways. This is one of the pitfalls of memorization, is where if you memorize the permutation formula as n factorial ways to arrange n things, there's loopholes in geometric counting. Now you might just memorize 10 different formulas for geometric counting, permutations, repeated elements, and just normal permutations with no repeated elements. But again, it's not going to work out. It's just simpler to understand what's going on so you can see what's happening better. Now, you know how to handle this geometric counting. Let's move on to combinations. Big part of combinatorics is combinations. Now, let's say we have a 7-people club, STEM club at school, and we want to choose a committee which oversees the STEM club. Alright, we have 7 people and we want to choose 3 of them, let's say 3 of them, to form a committee which oversees the STEM club, right? We have math, we have science, we have lots of different STEM things in our STEM club. Each student has their own specialization, and we want to choose out of randomly 3 students. Now, how many ways are there to do this? Well, let's just think about this. First, we have, and I'm going to label this. Alright, 3 ways. Now, let's choose the first person. The first person, when we're choosing the first person, we have 7 ways. And then we have 6 ways for the second person. And then we have 5 ways for the third person. And well, you could say this is just 7 times 6 times 5. If we compute the 6 times 5 first, that's 30 times 7, 210. But you'd be wrong. Here's why. When we're choosing a committee, in combinations, order does not matter. In permutations, order matters, but in combinations, order doesn't matter. So when order doesn't matter, we have some overcounting. Let's see how. Remember when we did geometric counting? Everything was counted 4 times because we have 4 seats. Now let's take a look at the combinations. We have a similar issue here. 7 times 6 times 5. We have 3 people we need to choose. And there are 3 factorial ways that we can choose these 3 people if order mattered. But order doesn't matter. So this is just 7 times 6 times 5 divided by 3 factorial, which is 3 times 2 times 1. And computing this, these cancel. We have 35 ways that we can do this. Now, 35 ways we can do this. We have a notation for this. This notation is used all across Combinatorics. The choose notation. We have 7 people choosing 3 of them. 7 choose 3 ways to build our committee. We have 7 people, and this is you just convert English into math. We're choosing 3 people out of 7, so obviously it's going to be 7 choose 3. This is read as 7 choose 3. Now this comes to a combinatorics thing. When we have 7 choose 3, this is just, well, we do 7 minus 1, the number of times over here. So in this case we have 3, so we go back 3, 7 times 6 times 5, to form a product with 3 numbers, including 7, minus 1, minus 1, and divide by the bottom number in factorial. And then we can cancel and divide out accordingly. So 7 choose 3 is the notation you would use. And get used to this notation. Like whenever you see a problem like this, express it in terms of this notation. 7 choose 3, and then compute it from there. Now, we need to discuss something. We need to discuss combinatorial identities. That's identities. Combinatorial identities. Suppose we have n choose k ways to order something. We can simplify this combinatoric by keeping the n constant, and then n choose n minus k. That's how we can simplify it. I'm going to give an example of this. Let's say we have 28 choose 27. How can we simplify this? Well, we keep the n constant, and then we compute n minus k. 28 minus 27, that's 21. And we see that the answer is just 28. It's so simple to simplify our combinatorics. So always make sure to simplify using combinatorial identities. This formula, you don't necessarily need to cram it in your head. It should be clear to you why this is true. And here's why. Let's see why it's true. Let's look at small numbers. Let's look at something like 3 choose 2. 3 choose 2 is equal to 3 choose 1 using this rule. But why? 3 choose 2 is 3 times 2 over 2 factorial. The 2's cancel out. The reason the difference is here is because the 2's cancel out, and each appearance of any further number will cancel out. But if we change this to 4 choose 2, we can't really simplify 4 choose 2 since 4 minus 2 is 2. So, in this case, it's just 3, which can be expressed as 3 choose 1. So always simplify using combinatorial identities. Now we've covered a lot of counting. Let's move on to the actual problem-solving techniques that you need for math counts. Now all of the details we learned over here, we learned combinations, geometric counting, permutations, repeated elements, combinations, combinatorial identities. You have to apply all those concepts to some problem types. Let's check out counting on a grid. Do my best to make a grid here. A small grid relatively, right? Let's just assume we have a grid, 3 by 3 grid. And go down like that. There we go. And I have point A here, point B. How many ways are there from getting from point A to point B if I go only to the down, go only down or to the right? The reason we're going only down or to the right is because this makes no sense. In problems, wherever it asks you the fewest number of like jumps or walks, you always assume it's down or to the right. Or if we were going from B to A, it's to the left or up, B to A. But this time we're going from A to B. So it makes sense that we're going down or to the right. Now let's solve this using one of my favorite techniques. We can only go down or to the right. Let's count the number of ways we go down and to the right. 1, 2, right? 2 down. And then from here we have 1, 2 to the left. To right, to right. We have 4 total movements. Now, how many ways can we choose 2 down? Well, that's just 4 choose 2 ways. And it turns out if we're only going 2 down or 2 right, we can't really simplify this. So it's just 4 choose 2 ways. And this can be simplified, 4 times 3, or computed, my bad. Multiplied by 2 factorial. 6 ways to get from point A to point B. Simple solution, how many total? And then we choose 2 to get to B. And we can see this is true by looking at a simple 2 by 2 grid. If we look at a simple 2 by 2 grid, we can only go, if we have point A over here and point B over here, there are only 2 ways we can go. We can go like this or we can go like that. And I'm going to use a different color. We can go like here or we can go here. Right? That's the number of ways we can go. But we can go there, but we have total 2 ways that we can go. Right? When we're choosing, we have 2 options. And then we're choosing one of the options to go. And then it's just 2 choose 1, which is just 2. And that's how we got our answer for this problem. Same thing here. We have 4, total we have 4. And we can go 2 down or 2 to the right. So we're choosing 2 down or 2 to the right. So if we chose 2 right, we would go like this. And then the only way you can go is down. All the way until you reach point B. But we can't go up or to the left. We can't go something we can't do is, I already mentioned this before, it's important to mention, because many people get confused, something like this, which is obviously, this is not allowed. So something like this would be allowed, but something like that would not be allowed. That's counting on a grid. Now, we're going to move on to the next topics with some problems. We're going to cover stars and bars, geometric probability, and counts, and stars and bars, recursion, and geometric probability. Now, it's good to always talk about probability when you're talking about counting, so I'm just going to talk about probability before we move on to the problems. Probability is the number of successful outcomes, or favorable outcomes, over the number of... So probability is the number of favorable outcomes over the number of possible outcomes. Favorable outcomes over the possible outcomes. Now, let's say what is the probability that if a fair coin is tossed once, what is the probability that we land on heads? Well, a fair coin will have two sides, and the probability that will land on heads is just 1, or the favorable outcomes is 1. Since if you list this out, the only two outcomes we have, possible outcomes, is H and T, and there's only one of that. So favorable is 1, possible is 2. The favorable outcomes is 1, the possible outcomes is 2. So that's simple probability. And this is basically all you need for entry-level math counts probability problems. The rest is all about looking at the problems. And it's good to learn some of these concepts just by the problems, like stars and bars and recursion should be just off of the problem, since recursion is really hard to explain even without looking at a problem, and it's really hard to understand without looking at a problem. So let's move on to the problems. Alright, so we have a problem here. At a grocery store, the grocery store people are giving away free apples for a holiday. Assuming the apples are all identical, how many ways can they give out 7 apples to 4 shoppers? This is a key example of stars and bars. The apples are all identical. Notice that this matters. Distinguishability matters. This is distinguishability. The apples are all indistinguishable. They're all identical. You cannot tell the difference between any two apples. In this problem, the only thing that matters is how many apples each person receives. And the bars comes in, we can separate the shoppers by bars. So 4 shoppers, well, we can have 1, 2, 3, we need a third bar. Well, 4 shoppers, 1, 2, 3, 4. And we can use 3 bars for 4 shoppers. Well, let's say this shopper got 2 apples, this shopper got 2, this shopper got 1, this shopper got 2. 1, 2, 3, 4. Every person got 2 except this person. That's one way we can do it. And what we're really doing is we're placing these bars at random. 1, 2, 3, 4, 5, 6, 7. So that it just randomly fits within. We don't care if one shopper gets 0, like 3 shoppers get 0, and the other person, 1 shopper, just gets 7. We just want to just place the bars so that the shoppers, so we distribute 7 identical apples to 4 shoppers, which are obviously indistinguishable people. Now, how many ways can we do this? We've learned combinations, we've learned permutations. What type of problem is this? Apply your skills. Let's take a look at the total things we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 bars. 1, 2, 3, 4, 5. So we have a total 10 items here, and we're choosing 3 of them to be bars. There are 10 choose 3 ways for this, and this is just 10 times 9 times 8 over 3 factorial. You can simplify. 10 multiplied by 3 is 30. We have 30 multiplied by 4 which is 120. So there are 120 ways they can give out 7 apples to 4 shoppers. We did this using stars and bars. Now, let's move on to the next problem. This problem comes from the 2020 MATHCOUNTS School Sprint. Problem number 23. If a fair coin is tossed 4 times, what is the probability of it landing heads up at least 3 times? Express your answer as a common fraction. So we're tossing the same fair coin 4 times, and we want the probability of it landing heads at least 3 times. So at least 3 times it needs to land up heads. Express your answer as a common fraction. Well, let's find the possible outcomes first. Alright, start off easy. And each coin has 2 possible outcomes, and each outcome for each coin can be paired up for each other outcome on each other coin, each of the 3 other coins. So this is just 2 times 2 times 2 times 2, which is 2 to the 4th power, obviously. So we have 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So we have our possible outcomes as 16. Now we want the favorable outcomes. The trick in this problem is recognizing the brute force solution as legitimate. What is the probability of it landing heads up at least 3 times? Let's try using a brute force technique by listing out a possible outcome, which is also favorable. Here we have HHHT. We can have heads 3 times. At least 3 times means we can have heads 3 times or more. So we have another possible outcome, which is also favorable, HHHH. Now, to find the number of possible favorable outcomes, HHHT, what do? How many ways can we arrange HHHT? Now, we already learned this in our permutations thing. We have repeated elements, 4 factorial. You have overcount of 3. If the h's were indistinguishable, we have 3 factorial ways to arrange them. If they were indistinguishable, 4 factorial is 24. 3 factorial is 6. So there are 4 ways to arrange HHHT, obviously. Let's look at HHHH. Well, there's 4 factorial ways divided by 4 factorial. You can already see there's only one way to do this. So, how many favorable outcomes? We have 4 plus 1, which is 5. So we have 5 over 16. And we notice that sometimes looking at the brute force solution can help us solve the problem. Let's move on. 2020 MATHCOUNTS School Sprint number 26. A lot of probability on that. 2020 MATHCOUNTS School Sprint. If 2 standard fair 6-sided dice are rolled, what is the probability the product of the 2 numbers rolled is a perfect square? Express your answer as a common fraction. So we have 2 standard fair 6-sided dice. So, possible outcomes. Each dice has 6 possible outcomes paired with the other 6, so we have 6 squared, which is 36 possible outcomes. What is the probability the product of the 2 numbers squared is a perfect square? Well, how do we build perfect squares? We square numbers. How do we square numbers? We need 2 of the same numbers multiplied. Now, we're all only looking at products. So, first, we have multiple ways of just 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, and of course 6 times 6. All of these result in perfect squares. We have 1, 2, 3, 4, 5, 6 favorable outcomes 4 if we roll this double the same number, or the same number twice. And then we take the product of that, we're going to get a perfect square. Now, what other perfect squares can we get within 1 to 6 by rolling some products? Well, it could be over 6 as well. We need to combine these so we roll a perfect square. Now, what are the perfect squares between 1 and 6? Well, 1 is not 2, 2 is not, well, 1 is. 1's a perfect square, already did that. 2 is not, 3 is not, 4 is a perfect square, 5 is not, and 6 is not. So 4 can be expressed as 1 times 4 or 4 times 1. Order matters since we have 2 standard fair 6-sided dice. And there are 2 possible outcomes for this, so total we have 8 favorable outcomes currently. Now, are there any other products that could result in perfect squares? Well, there are none. If we pair the products together, there is no way that we can generate a perfect square other than actually squaring the numbers. 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, and then 4 is 1 times 4 and 4 times 1. If you want to try for yourself, we can try it right now using a quick brute force technique. We have 1 times 4, which already counted, but 1 multiplied by anything other than 4 does not result in a perfect square. 2 multiplied by anything other than 2 does not result in a perfect square. 3 multiplied by anything other than 3 does not result in a perfect square. 4 multiplied by anything other than 4 does not result in a perfect square. 5 multiplied by anything other than 5 does not result in a perfect square. And 6 multiplied by anything other than 6 does not result in a perfect square. If you know your multiplication tables, this should be clear to you why there are only, over here we have 6, plus 2 over here, 8 favorable outcomes. Now we just simplify this down. We have 4 multiplied by 2 is 8, and 4 multiplied by 9 is 36, so the probability that the product of the two numbers rolled is a perfect square is 2 9ths, 2 over 9. Now let's move on. From a regular octagon, it's taken from the 2018 AMC 8 number 23, one of the harder problems on the test. From a regular octagon, a triangle is formed by connecting 3 randomly chosen vertices of the octagon. What is the probability that at least one of the sides of the triangle is also a side of the octagon? So let's construct an octagon first. Octagon has 8 sides, 8 vertices. Regular octagon, so side lengths and angles should be equal. We don't really care about the side lengths or the angles, though. This is another example of geometric counting. But we're also using probability, so you could call it an application of geometric probability, but geometric probability is a little bit different than this, but we'll slide with it. A triangle is formed by connecting 3 randomly chosen vertices of the octagon. What is the probability that at least one of the sides of a triangle is also a side of the octagon? Let's see how possible cases that at least one of the sides of a triangle is also a side of the octagon. Let's take a look at this. So let's choose this vertice right here. And let's build triangles. Side of the triangle is also a side of the octagon. And we can draw a segment to here, not the best triangle, but works out. We can draw a segment from here to this line, to this vertice, and it also results in the shorter side of the triangle being the same side, sharing a side of the octagon. We can have another one over here, and we can have one over here. Now, we want to count the possible outcomes first. And the possible outcomes is pretty simple. 3 randomly chosen vertices of the octagon. Well, how many ways can we form the triangle? That's just 8 choose 3 ways, which is 8 times 7 times 6 over 3 times 2 times 1 3 and 2 cancel out to 6. We have 56 possible outcomes. 56 triangles can be built. Now let's check out each vertex. 1, 2, 3, 4, 5, 6. Now we have 8 vertices, so you could conclude that 40 out of 56 is the probability. But take a look at this. When we're on this vertex, we can build another triangle like that. And we can build another triangle like that. And from this vertex, we can also build more triangles like this. And for each of the vertices, we're counting everything 8 times. Again, this is another application of our geometric counting. Look, I'm going to show you the geometric counting we did. The geometric counting that we did shows how over here, the circle, if we rotate the table, we might get 4 times, because we have 4 seats, that we're going to get 4 times the number of things we want to count. So if we go back to our origin, to our problem that we're working on right now, we have 8 vertices, and this can be repeated 8 times. So the way we're going to solve this is, each thing is going 8 times. But we also notice that this is not a valid conclusion, right? This is not a valid conclusion because I want you to take a look at this problem. Each vertex forms 1, 2, 3, 4, 5, 6 triangles. Take a look and see if you can conclude by solving the problem. I'm going to pause the video because this is a very interesting problem. 2018 AMC 8 number 23, very interesting problem. So I want to give you the opportunity to solve it on your own before continuing. Alright. If you've noticed by now, we have an overcount of 48, right? Because each one can form 8 more of the same triangles. But remember, there's only 8 more triangles of the same thing that can be formed. So in this case, an application of geometric counting is we're subtracting off 8. Because if you look at it, the overcount is not 8 times each vertex, it's just 8 triangles. Since we have 6 triangles over here, we can build more triangles other than this. We can connect these, and we can repeat the triangles 8 times, but 8 triangles are being repeated. So we have to subtract off the overcount, which results in 40 over 56. Now we simplify this. 8 times 5 is 40, 8 times 7 is 56. So we see the probability that at least one of the sides of a triangle is also a side of the octagon is simply 5/7. Another application of geometric probability and counting. Let's move on. 2019 AMC 8 number 25 turned out to be a little bit easier than expected. Alice has 24 apples. In how many ways can she share them with Becky and Chris so that each of the people have at least 2 apples? A fairly easier problem for the last problem on the AMC 8 2019. But let's just take a look at this. We have 24 apples. I'm not going to draw every single one, but I'm going to draw 6, since 6 times 4 is 24. And of course, we have more. And I'm going to end with 2, since each of the people need to have at least 2 apples. Now, how many ways can she share them with Becky and Chris that each of the people have at least 2 apples? The apples are all identical, and we go back to our stars and bars technique that we used on the first problem. Right, the first problem we used our stars and bars technique that we learned. Now, this is another crucial application of stars and bars. A basic stars and bars problem is applied in this problem. See if you can figure it out for yourself. This is an interesting problem in the sense that it's not your basic stars and bars problem. You don't just place in your bars. Alright, Let's take a look at the two balls, or the two apples we have. The two apples that we have outside, each person has at least 2 apples. Let's look at the simplest case. That Becky and Chris get 2 apples, but then Alice gets 20 apples, since we have 20 minus 4. Alice gets 20 apples. But notice how we can't place any of these bars anymore to the right. Like, we can't place this over here, we can't place this over here, we can't place this bar over here. The bars have to be in this position, or we can go closer to each other. Essentially, we've lowered our workload to 20 apples, and how many ways can we split that up? And this, we've simplified this to, we have 20 total apples, and we're essentially choosing the bars to be in the apples, right? We're choosing our bars. Right, so over here what I'm going to do is we are going to apply the stars and bars technique and see if you can take it off from here. Alright, 20 apples, choosing 2 of the bars to be in the apples. Now this could be written as 20, choose 2, ways, which is just 20, multiplied by 19, over 2, factorial. We just cancel. 19 times 10 is 190. So there are 190 ways that she can share them with Becky and Chris, that each of the people have at least 2 apples. Classic implementation of the stars and bars technique. Let's move on. 2019 Math Counts School Sprint number 25. 2019, not 2020. Kermie starts on the lily pad at location A and moves to the lily pad at location B with a series of hops made only to adjacent lily pads while traveling along the dashed segments as shown. If Kermie uses the fewest possible number of hops, how many ways are there for him to get from location A to location B? In this problem, we can only travel along the dashed segments, or the lines that we've drawn in this entire grid-like figure. Those are the only ways we can travel along the figure to get from point A to get to point B. Kermie uses the fewest possible number of hops. Remember, we discussed this. If we're getting from A to B, we only go down or to the right. Right? We don't go up, because that would be a waste of time. Unless we're over here and we need to get from here to here or here to here. Then we can go down or up. So we could go up, but we can't do this. We can do this, but we can't do that. We cannot repeat the same thing. So fewest possible number of hops, that's what we're dealing with. So let's solve the problem. How many ways are there from get to location A to location B? The trick in this problem is recognizing this entire massive complicated grid as 3 separate grids, right? We have grid A, we have grid over here with A, grid over here, and we have grid over here with B. Let's solve A first, and what we're going to do is we're going to get A all the way down to this point. We're going to get A to this point. We'll call this point C, and then we're going to get from C to this point over here, which we'll call point D, so that we reach A. That means we reach B. Now let's solve. Now we can go down or to the right for this grid. So solve 1, 2, 3. And go 3 down. 1, 2, 3, and 3 to the right. So there's 6 choose 3 ways to get from point A to point C, which we can just compute as 6 times 5 times 4 over 3 factorial, which is just 20. Point A to point C, that's 20 ways. Now, point C to point D. Notice how I talked about how we can't do this. The fewest possible number of hops. In this case, it's the same level. We can only go to the right. We can't go down. We can't go to the left. Only right. And there's only one way to do this. So we have one way to get from point C to point D. Now we reach D to B. We can already list out the 2 ways we can go. And there are 2 ways to get from D to B, right? 2 ways to get from D to B. Now, how many ways are there from get to location A to location B? For each of the 20 ways from location A, we can pair each of the 20 ways with only one way over here, so that's just 20 times 1. And we can pair each of the ways in the first grid with each of the ways in this grid. So this can be computed as 20 multiplied by 1 multiplied by 2, which is equal to 20 multiplied by 2, which is 40. There are 40 ways to get from location A to location B. Let's move on. In my opinion, learning recursion is just about the problems. So we're going to solve a problem using recursion. We're going to use a recursive solution for this problem. Every day at school, Joe climbs a flight of 6 stairs. Joe can take the stairs 1, 2, or 3 at a time. For example, Joe could climb 3, then 1, then 2. How many ways can Joe climb the stairs? So we have a flight of 6 stairs. It's a classic recursion problem. 6 stairs. Right, so we have 0th step, 1st, 2nd, 3rd, 4th, 5th, and the 6th step. And Joe climbs this flight of 6 stairs. Joe can take the stairs 1, 2, or 3 at a time. For example, Joe could climb to get from step 0 to step 6. Joe could take them 3 and 3, or 2, 2 and 2, or just 1, 2, 3, 4, 5, 6. For example, Joe could climb 3, then 1, then 2. How many ways can Joe climb the stairs? Now we could do a massive list of the number of ways if 1, 2, 3, but that would take forever. And a much simpler solution is looking at the recursive solution. How many ways are there? And this is denoted as F0. How many ways are there to get to the 0th step? To get to the 0th step, there's only one way. You're already at the 0th step. Let's move on. F1. How many ways are there to get to the 1st step? Well, Joe can climb 3, 1, or 2. We can't go 3, 2, or 2, so we only have one way, which is like this. So we only have one way for F1. Let's look at F2. How many ways are there to get to the 2nd step? Now to get to the 2nd step, we have multiple ways. We can go 1, 2, or 1, 2 steps, and the 2nd step is actually over here, so that would be a 3rd step. We can go 1, 2, or we can go something like 2 at a time to get to 2. So we can take 2 at a time, or we can go 1, 2. And those are the only possible ways I see coming. We can go 1, 1, or just 2 at a time. So there are 2 ways for F2, F2. There are 2 ways. Now F3, we can take 3 at a time. We can take 1, 2, 3. We take 3 at a time. We can take 2, 1, or 1, 2. And we realize there are 4 ways to get to the 3rd step. Now check this out. Joe can take the stairs max 3. Look at our pattern. We added 2, 3, and 4 to get 4. Now let's see if we can build a formula. What is F4? Now if our formula is true, we should be adding F3 plus F2 plus F1. This is how recursion works. We're building a formula so that we can compute the answer quickly. F4 can be denoted as how many ways can get to F4? Well, we can 1 at a time, 2 and 2. We can take 1, 3, or 3, 1. Alright, 1, 3, 3, 1. Or we can take 1, 2, 1, 1, 1, 2, or 2, 1, 1. Now we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. And our formula is working. We have 4 plus 2 plus 7. And now F5, built a formula. We have F5 is F4 plus F3 plus F2, 7 plus 4 plus 2, 7 plus 4 is 11, 12, 13. And our answer is just F6. We want how many ways can Joe get to step 6? Well, the sixth step is just 7 plus 13 plus 4. 7 plus 13 is 20. 20 plus 4 is 24. So there are 24 ways to get to the sixth step. That would take a lot of time if you just listed out and used a table or a diagram. So F6 is 24. And that is how many ways Joe can climb the stairs, and our answer is E. That's the applications of recursion. We start at the 0th step and we get bigger each time until we reach to the step we desire. So this concludes our long lesson on probability and combinatorics. Hopefully this lesson was helpful, and yeah.